Okay. Exams are almost done. I'll get those done quick. Remember what I'm doing is I'm checking your confidence interval question to your previous chapter. Could possibly get you some more points. So give me a little time for that and I'll get caught up soon. Not a whole lot we got to go through here. Not a whole lot we got to go through here. You know 85% of it. We got to change a couple of things. So, yeah, there's only 2 sections in this one. So today's one, Wednesday's the second section. We'll kind of see from there where we're going. Last year I put 10 and 11 in one test, but we'll see how it goes. So, estimating a population mean. I'll jump right into the formula. You guys know that the formula is in words, okay? It's a confidence interval. So it's a formula in words. Last chapter, or not, sorry, 2 chapters ago, statistic was p hat, our critical value was z, and our standard error was p hat 1 minus p hat over n. Okay, that was last, or 2 chapters ago, with proportions. So now it's our job to recognize, is it going to be categorical data or is it going to be numerical data? Okay, all of this stuff in this chapter is numerical data. However, I may throw categorical stuff in on your test, right? Just recognize those type of things. So what's going to change now is we're going to change from this formula to means. So instead of p hat, we are now going to have x bar. Okay, not a big deal. It's still a statistic. Statistics come from samples, and so that's what x bar is. It's a completely different than p hat. Okay. For right now, I'm going to tell you that that's z, but it's not going to be z. We'll change that. And then the standard error now is no longer p hats. It's the standard, or the standard deviation, which is sigma over the square root of n. Okay? Well, this gives us some problems that we're going to have to talk about for the next 5 or 6 slides. Okay? So this formula is not going to be our formula because of some certain changes, but that's kind of what we're looking at. Okay? Remember that sigma is the population standard deviation, right? That's the population standard deviation. Well, in order to know the population standard deviation, we have to know the population mean, which we don't. Because if we did, we wouldn't have to do a confidence interval, because that's what we're trying to find, is the population mean. Okay? So we're doing a confidence interval because we don't know the population mean, or we don't know mu. Well, if I don't know mu, it's impossible for me to find sigma, because sigma is x minus mu, right? Well, we don't have that. We have x minus x bar, which is the standard deviation, or x minus x bar squared all over this, right? So instead of sigma now, that's going to be s, okay? So because we don't have sigma, we can use the only thing we're going to have is our standard deviation from our sample. Okay? Our standard deviation from our sample. Well, now picture this, right? Using S as opposed to sigma gives us some issues. Okay? It gives us some issues. So let's just look at these issues really quickly. A farmer wants to estimate the mean weight of all the tomatoes on her farm. To do so, she takes a random sample of 4 tomatoes, calculates the mean weight, and uses the sample x bar to create a 99% confidence interval. Okay, with all that stuff, so we're going to get 4 tomatoes. That's not a very big sample. We'll probably need bigger than that, right? Suppose that all the weights on the farm are approximately normally distributed. Let's say that has a mean of 100 and a standard deviation of 20. Okay, so let's just go to this really quickly. Just kind of watch what happens. Means. This is z with s, right? The standard deviation. The population mean is 100. The population standard deviation is 20, or the sample standard deviation is 20. The sample size was 4, right? Sorry, that was supposed to be a 4, not a 10. 4, okay? and I'm going to take 100 of these. So there is 100 confidence intervals. Okay with that? 100 confidence intervals. Well, I did a 95% confidence level, and knowing the definition of a 95% confidence interval or level, I should collect the population mean 95 out of 100 times, right? 95%. I'm at 91%. I missed it 9 times instead of 5 times. Yeah, that sometimes happens, right? So let's do another one. I'm at 83%. I'm way under 95. Do another one, 81%. Out of doing all these, I'm just at 85%. I'm supposed to be at 95%. Fair enough with all that stuff? So by using S, we're having some issues. We're not capturing it as many times as we're supposed to. And I can do that as many times as I want, right? Population, we're at 85%. And even if I do a larger sample size, I'm still going to miss it more times than I'm not supposed to, right? It's okay to miss it. I just shouldn't miss it as many times as I am. Okay? Everybody follow along with that? So that's where we're at. Problems with using Z. Problems with using Z. Since we don't know the population mean, we don't know the population standard deviation. I've kind of emphasized this 3 or 4 times. This is what's new, and this is why you have to understand why we're doing what we're doing. Now we're trying to estimate 2 parameters. We're trying to estimate mu along with sigma, right? So I'm estimating mu with X bar. I'm estimating sigma with S, okay? We're introducing more variation to the standardized test statistic, which is normally Z, okay? Thus, anytime we are dealing with means, we change from a Z distribution to a T distribution, okay? We change from Z's to T's. So now you need to know anytime we're dealing with means, we are dealing with T's. You need to know why we're dealing with T's, and it's because I'm estimating the standard deviation. I'm estimating the standard deviation of the population. I've got too much variability in there. Too much variability in there. And so I'm going to use T's as opposed to Z's. So instead of Z star or Z, whatever that is, right, we're going to be using T. All right, so let's talk about the differences between T's and Z's. T distribution is still bell-shaped. It's still centered at 0. So it's still bell-shaped. It's still centered at 0. Okay, so there's not much difference there. It's still bell-shaped. It's still centered at 0. T distributions are more spread out. They are wider. So if they're wider, they're not as tall. They're more spread out than a Z distribution. T's are more spread out because there's more variability. There's more variability. We're estimating too much stuff going on. So I have more variability. T distributions are distinguished, by a positive number called DF, or degrees of freedom. Okay? Their distributions, they're distinguished by DF. So T distributions change, right? The Z distribution is a Z. It's always 0, 1, 95% is always 1.645 or 1.96. 90 is always 1.645. 99 is always 2.576 or 54 or whatever those numbers are, right? Those are always there. T's are going to change. T's are going to change depending on what these degrees of freedom are. And we can abbreviate degrees of freedom with DF. Okay, we're going to abbreviate it with DF. As the number of degrees of freedom increases, when degrees of freedom increase, the spread of T's will decrease. So as degrees of freedom increase, you can kind of think of it as sample size. As your sample size increases, your variability decreases. As your degrees of freedom increase, this spread will decrease. And if it decreases, it's going to make it taller. Okay? And at some point, those t distributions will become a z distribution. At some point, a t distribution will become a z distribution. So, what all we need to know about that, there it is, okay? You can see on your page, just right over from that, the different z distributions, or the different t distributions with the z distribution. It will come up in my next slide. But t's are just like z's. There's no difference other than really they're fatter. There's more area in the tails. They're shorter. They're different with degrees of freedom. Degrees of freedom are going to change. So we'll spend a couple slides on degrees of freedom here in a second. But degrees of freedom are going to change those t distributions. They're going to change those t distributions. It's still bell-shaped. It's more spread out. Degrees of freedom are going to change. Each degree of freedom is going to be a different t, but they're always centered at 0. It just squeezes it in as degrees of freedom increase. As degrees of freedom decrease, it spreads it back out. So it's going to change. It's going to fluctuate with these degrees of freedom. Okay, z's stay the same. Z's stay the same always. Okay, here you can see this purple one is a z. It's the tallest and it's the most narrow. It's the tallest and it's the most narrow. The red one is a 2 degrees of freedom. It's the shortest and the widest with more area in the tails. There's 9 degrees of freedom is the middle one. Okay, just to kind of give you an idea. You will never have to guess what any of this stuff looks like. You just need to kind of somewhat understand that T's are wider. And what I mean by wider is they really have more area in the tails. Okay, it's hard to see how much wider they are here. It's really down here in the tails because they're shorter. Okay, so they're shorter. All this kind of comes close to staying the same. It's just this area down here. That's where it starts spreading out. Okay, this is the least degrees of freedom. Here's more degrees of freedom. There's a Z. If I up that to 10 or 12 or 14, that blue would get closer and closer to that violet or purple or whatever color you want to call that. Y'all okay with those? T distributions have more area in the tails than a standard normal distribution. Standard normal distribution is nothing more than a Z. Any question about a T? Any question about a T? All right, so now we need to talk about these degrees of freedom. Okay, this might be one of the harder things we have to do in class. So to calculate degrees of freedom, it's a formula we got to know. It's not on your formula sheet. It's not on your formula sheet. So I'm going to tell you how to calculate these, right? First, you have to know the sample size. You got to know the sample size, and they're probably going to tell you what the sample size is, right? Typically, they do. Typically, they tell you we have a sample size of 4 tomatoes. We have a sample size of 20 tomatoes. We have a sample size of 200 students, right? So you have to know the sample size. Many of you guys are going to have to turn your calculator on. I don't know how many of you will have to, but there will be a lot of you guys that have to turn your calculator on. And I tell you that why? Because it takes too long for those things to boot up, right? So you're going to enter that sample size on your calculator, whatever that sample size is. Again, they're going to tell you what it is, or you're going to be able to see the data, but it's not going to be a secret is what the sample size is. So you enter that sample size. Let's say it was 4 tomatoes. You hit 4, okay? And then you go over to that side on over here and you hit that minus symbol. The minus symbol. Don't hit the negative. Don't hit the negative. You hit the minus. You hit the minus, okay? When you get done with that, you're going to type in a 1. Hit enter. That's the degrees of freedom. N minus 1. But it's not on your formula sheet. I hope not. And guys, hopefully that does make a little bit of sense because as I told you earlier, think of it as your sample size. You know, as your sample size increases, that decreases your standard error or your standard deviation. Well, DF is pretty much that sample size. Okay? It's just minus 1. It's minus 1. Okay. Guys, you don't have to tell me that DF equals N minus 1 or DF equals. But you do have to list it. Okay? So that's one extra step you guys are going to have to do for confidence intervals for means that you didn't have to do for proportions. Right? Proportions, we would write down p hat plus or minus z square root p hat 1 minus p hat over n. Now you got to write down x bar plus or minus t, and then you got s over the square root of n. But then you have to tell me what df is. You have to tell me what df is. Let's figure out how to find this t star critical value, because that's important. We got to know how to find that critical value. Okay? So let's say that we have a 95% confidence interval, SRS of 12. SRS of 12. So if it's an SRS of 12, we know immediately that DF is 11. Okay? So you're going to do this two different ways. You can go to the table. Truth be told, this might be easier than using your calculator. Okay? It's almost easier to go to the table on this, right? We're going past these formulas. We're going past these formulas. You're going past the z's because it's no longer z's. Those are the negative z's. Here are the positive z's. And then the next group are the t's. You'll see the t star critical value. Well, if it's 95%, guys, it's pretty easy. We just go down through here and we find 95%. And then you'll go up because over here is your degrees of freedom. Okay, and so you're going to go up until, what was this, 19? It was 12, so we got to go to 11, yes? So I'm going to go 95 is right here, and I'm going to go up to 11, and I'm going to see that 2.201 is DF. N minus 1. It doesn't say N, it says DF. Okay? Let me tell you a couple things about the table, right? We do know that your calculator will be a little bit more accurate than the table, but the table works. The table, you can see, goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, but at 30, you'll see it jump from 30 to 40, and then from 40 to 50, from 50 to 80, 80 to 100, 100 to 1,000. Okay, and the reason for that, guys, is these numbers are changing so small that you really don't notice it. So if your sample size was something like 80, or let's say 72, well, 71 is not over here. So you just back it up until you get to 60. Just back it up until you get to 60. Okay? I'm going to show you. Yes, sir. You just keep backing it up until you get there. Yeah. So even if it was 79, back it up to 60. Because again, the difference is 1.676 and 1.671. I mean, 0.005. You're not really talking that big of a difference. Y'all okay with kind of making sense on that? And if you feel real uncomfortable about it, then you just use your calculator. We can use your calculator to find it exact, right? Yeah, 1.671, 1.664. So like I said, there's 0.007 difference. And if you want to, I mean, you can almost guess and put a number there. This is not that big of a deal, right? Just notice it's different than the z-score, because the z-score is all the way down here. That's infinity. See how it says infinity? If your n was so big, it might as well be a z-score. It might as well be a z-score. And so those z-scores are on the bottom down there. I mean, if you had a sample size of 9,000. So a sample size of 9,000, I might as well just use the z-score. Most time you don't see them that big, but any questions about that the t critical value other than your calculator, which I'm going to show you how to do it on calculator here in a second too. Okay? On your calculator, dang it, I meant to turn that on. On your calculator, if you want to use it, that's fine. I just see students mess up a lot, okay? And the reason for messing up is, remember how your inverse norm has a left, center, right? These t's don't have a center. They don't have a center. And so when you use your calculator for a 95% confidence interval or level, okay, second distributions. Well, I don't want inverse norm because it's not a T, or it's not a Z. I got to use T, inverse T. So when I hit enter, it tells me the area. Well, that's where you got to be careful, because if it's 95, it's the middle 95. You got to add that tail. You got to add that tail. So 95 gives me 5%. 5% left over is on both tails, so it's 0.025. So I can either punch in 0.025 or 0.975. 0.025 is going to give me the negative t. The 0.975 is going to give me the positive z. We got to enter the df right there, which we said was 11. We got to paste it. And then that's going to give me that t critical value. Okay? The one I just found on that table. Now, everybody okay with this? Just you gotta remember to use that stupid tail, because if you punch in 9.5, you're gonna get the wrong one. Okay, so yep. That's a 95. Okay, if they want 95, they'll tell you what they want right here, right? Typically it's 95, sometimes it's 90, sometimes it's 99, sometimes it's 86. Well, if that's 95, then what's left over? 5%, but it's 5% for both tails. So it's half of the 5%, which this side over here now is 0.025, and this side will be 0.025. Well, if I do inverse norm 0.025, that's giving me this one. If I do 975, that's going to give me this one. Will it always be what's left over? Yes, it's always what's left over. Divided by 2. Which is what? Go ahead. Well, because the center is 0. Is that right? I'm taking my X bar and I'm adding and subtracting the standard deviations. It used to be 2, right? For proportions, it was 2. If 95, it was 2, 1.96. This one's a different number so that I can capture more of them. It's a little bit wider. Those of you knuckleheads that we put on this critical value program, notice how it says proportions are means. Well, now if you go to means, what's the confidence level? What was that, 95? And then it asks for the df, which is n minus 1, or n minus 2 of its slope, which we're not there yet. So the df was 11. It'll give you the t-score. It's plus or minus on the formula. I mean, the formula's x bar plus or minus. That's why it's plus or minus. Okay. Again, kind of showing you on the table right here, right? You go up until you see that 11, you'll just go across. There's that tail area that we talked about too. So if you're less concerned about the table doing it and you want that 95, guys, if you go all the way up to 95, it tells you that 0.025. It gives you that tail area there too. Okay? Again, just make sure you're understanding all this stuff. It's not that difficult, but guaranteed there's a question on this test. There's several on the homework tonight of what is the critical value for this scenario. Okay. Here's inverse t. That's 1 year I asked, why do I have to punch in 0.975 on my test? Or what other value could I use? 0.025. 0.025 will give you the negative, 0.975 will give you the positive. Okay? So here's another one, a 90% confidence interval, random sample of 48. So if I have a random sample of 48, the first thing I put in my head is DF is equal to 47. Okay? DF is 47. So I could go to my table. Whoops. So if 47 is not on there, then I got to go to 40. So 90% is here. 47, so 47 is not on there. 40 is 1.684. This is 1.676. So it's somewhere in between there. You're welcome to use either one. You won't have a multiple choice where it would choose something that close between it. Okay? If you feel comfortable about it and you would rather use your calculator, then we can use the little program, right, which will actually do it exactly because it, yay, he loves you, you owe him Cheez-Its. I updated it. If you do inverse t, 90% leaves me 10% left over, which each one is now 5%. And we'll do 47. Paste it. Negative 1.678. Okay? Beautiful. Boom. Okay, so get comfortable with finding that t critical value because it is different. It's not like the z where if it's 95, it's 1.96. You know that. These change. These change with the degrees of freedom. Okay? The conditions for estimating mu are not real different, but they're not exactly the same. So the conditions, let's talk about them. There's 3 conditions. There are 3 conditions. The very first condition I always want to make sure we get is an SRS. Okay? Make sure we have a simple random sample or the data is coming from a good population or it's not biased, basically, right? We don't want the sample to be biased. We still check the 10% condition provided it's not an experiment. Provided it's not an experiment, we still check it. Okay? And then the large counts is big time difference because there is no n or p's. There's n's, but there's no p's. We can't do n times p. So the large counts is a little different for this one. And there's going to be one of 3 ways to show me the approximately normal or the large counts. Okay? One of 3. So here's the first way it's going to be. The population is normal. They'll just tell you the population is normal. If you guys can think back to sampling distributions, if the population was normal, it didn't matter what my sample size I grabbed from it. It was normal. It didn't matter if my sample size was 1 or 2 or 3 or 4 or 2,000. It was all normal if the population is normal. This one happens very, very, very rare because most of the time we don't know what the population looks like. So that one happens rare, okay? Another way is the sample size is large enough. Hopefully the sample size is larger than 30. Y'all remember what theorem that was? Central limit theorem, okay? CLT. The central limit theorem stated that as long as my sample size was large enough, and we said 30 was our number, then it doesn't matter what our population looks like. It doesn't matter what our population looks like. If my sample size is 30, the sampling distribution will be approximately normal. Okay? And then here's the third way, and this one's the one that gets most everybody, right? Let's say it's not 30, and we don't know what the population is. Let's say they give you the data. They give you the data from your sample. If they give you the data from your sample, you have to graph that data. You have to graph it. It should not look very strongly skewed. It should not have outliers. It should not have gaps. It should just look like a good set of data. And what's a good set of data? Well, it's probably going to depend on what your sample size is. Okay? If the sample is small, less than 30, we're going to graph that data that they give us. I always use a box plot. I use a box plot. They will use stem and leaf plots. They will use bar graphs. They will use several things to graph these with, as long as it's just not blatantly obvious that it's just bad data. Then we'll say it's approximately normal, or we'll go with it. One of those three has to happen. If one of those three does not happen, guys, I cannot count, or I cannot calculate that T critical value. I cannot calculate the T critical value. If I don't know what the population looks like and my sample size is less than 30 and I graph that sample data and it's bad, I can't do these. Okay? One of those three will happen. One of those three will happen. 10% still there. You want your sample to be less than 10% of your population, and then you want the randomness. So it's still the same three conditions. It's just, again, this normality, or the large counts, or whatever you guys want to call them, okay, that's different for every single one of these that we do. It's different for every single one of these we do. These for sure are not n times p, because you only have a p. So I can't check n times p greater than 10. Y'all okay with the conditions? Tell me if the large or normal count is met. To estimate the GPA of students at your school, you randomly select 50 students. Is that normality okay? Because your sample size is greater than 30. They drew the bar graph over here, but I don't even need it. That bar graph's okay. That's okay. That doesn't show me any big outliers. It does look somewhat normal. Yeah, there's a couple gaps in there, but that's going to happen because our data is not very big. We also recognize, I think we're okay, but I don't even look at it. I'm over 50 or I'm over 30, okay? So my sample is 50, that's greater than 30, I'm okay. Determine if the normality is met for this one. How much force does it take to pull wood apart? The stem plot shows the force. 20 randomly selected. So the first thing, guys, I don't know what the population looks like, which, again, most of the time we don't. My sample size is not large enough because I only got 20, so I've got to look at that data. And that data is way strongly skewed. Way strong skewed, and not only is it strong skewed, it's got several gaps in there. So this one does not meet the criteria. The stem plot is strongly skewed to the left, possible low outliers. Possible low outliers at 23. Bless you.
Thank you.
I got another one here. I want to estimate the mean SAT math score at the large high school. Box plot of 20 randomly selected students. Well, again, I don't know what the population looks like. Most of the time we don't. I didn't get a large enough sample. I only got 20. So now I'm going to look at that box plot. It's slightly skewed, but not enough. I'm okay with that box plot. I'm okay with that box plot. And so I would say, because the box plot does not look crazy, or it looks somewhat normal, or it looks approximately normal, I'm going to go with it. I'm going to go ahead and use it. It's okay. Even though 20 is less than 30, the box plot only moderately skewed to the right. There's no outliers. That's why I use box plots, right? They show outliers because of the modified box plot. This does not have any outliers. So we're okay with that one. Again, it's slightly skewed, but not enough. not enough. It would have to be really, really long tail, and it won't be a really long tail because at some point those will be outliers. Okay. So if you're asked to construct and interpret a confidence interval, you must show evidence, I've emphasized that enough, that the conditions are met. Show evidence that the conditions are met. Okay, here's how we're going to do them. The method, well, it's going to be a 1 samp t interval. A 1 samp t interval. It's not going to be prop. 1 samp mean t interval. 1 sample mean, because we're dealing with means now, we're not dealing with categorical data. Every time we're dealing with means, we do with t's. As soon as you see, and as soon as you think it's means, it's now t's. It's never z's with means. If it's a z, that implies we know the population standard deviation. If we know the population standard deviation, we have to know the population mean. If we know the population mean, we don't have to do this. So that you won't ever do z's with these. Okay? The conditions, verify each one of them is met. There's 3 of them. There's 3 of them, provided it's not an experiment. If it's an experiment, there's only 2 of them. We don't check the 10%. Okay? Showing the large counts or the normality is the toughest one. Okay? That's the toughest one. If it's over 30, you don't care. If the population is normal, you don't care. Those are easy to show. If it's under 30 and you have the data, you have to graph it. Okay? And I just graph it with my calculator and then show that graph on my paper. Calculations, I still show the formula, I still show the values, and then I have to show the interval, but I didn't put it on there. But make sure you list the DF also. You've got to show the DF. They will ding you for not showing DF equals. And then our conclusion is the exact same conclusion we wrote 2 chapters ago, except we're not going to write the word proportion, right? We are 95% confident that the true mean, we're not going to write the word proportion because it's not proportions, it's mean. That the interval from here to here captures the true mean context. So we already know this stuff. We already know all this stuff. It's just you got to know the differences. You got to know the differences. And the biggest difference is these are means, they're not categorical data. It's not proportions. So if it's means, well, that means I got to use x bar. And that means I got to use s sub x. And I still got to use n, and now I got to use t instead of z's. And if I use t's, I got to write down df. And then how I prove normality is different. The method's going to be different words, but it's still 1 sample. It's a mean. And when I say means, I'm always use t, and it's an interval. Next chapter, it's going to be 1 samp mean t test. Conditions are still going to be the same. The calculations, right? You're going to show the formula with the values. Show the formula, then show the values, then give me the interval. And then we write our conclusion, right? There's intervals. Intervals don't have hoes and ha's. Intervals don't have hoes and ha's. Chapter 8, we learned that 73% of American adults claim to have read a book on the previous 12 months. This was based on a 2016 Pew Research Center that interviewed a random sample of 1520 American adults. The same study also reported that on the average, the number of books read by members of the sample, including those who reported, look guys, they give you, I'm telling you, they give you X bar right there. It's not a p hat, it's telling you its means. And not only do they give you X bar, they give you the standard deviation of the sample. Very nice of them. They give you all the information. I really don't need anything. The freaking sample size is ginormous. Construct and interpret. That means I got to do the full-blown thing. 95% confidence interval. Look, I told you. They'll even put it again. Mean number of books read by Americans in the previous 12 months. How many was it? 1520. 1520 is less than 10% of all adults. 1520 is a whole lot bigger than 30. And starting now, if you want to say large counts condition, or if you want to say approximately normal, I don't care. But one of those, either approx normal or large counts. I still like approx normal. But if you want to say large counts is okay. Don't just do this and leave it. Okay, so there's my three conditions. So I'll go right to x bar plus or minus t s sub x square root n. All that's on your formula sheet if you know it, where it is. That's your sample statistic. That's your critical value. Your standard error of the statistic is s sub x over the square root of n. And they told us all these things. They told me x bar was 12. They didn't tell me what t is. I got to find that. They told me what s of x was. That's 18 over the square root of 1520. What was it, 95%? So let's go to my little calculator here. And I'm going to do program, critical value, enter it. It's means 95 at 1519. 1.96, same thing as a z-score. Because the sample size is so darn large, it's a z-score. It might as well be a z-score. So it's 1.96. And then, guys, I'm going to go stat. Oh, I guess I got to hit enter to get out of here. Enter. Clear. Stat. Tests. It's not a test. It's not a test. It's not a test. There it is, t interval. It doesn't say 1. It just says t interval. Enter. Okay? Do I have the data or do I have the stats? Well, this time I have the stats. Your homework tonight is going to give you the data a lot. If it's data, where's your data come from? Hopefully you put it in L1. If you put it in L2, then change that to L2. That's second 2. Second 3 is L3. Second 4 is L4. Okay? But I don't have the data. I have the stats. So they want to know what X bar was. 20? 12? S sub x was 18. That's a big standard deviation. There's 1520. Now, don't put 1519 right there. Careful. So they'll try to trick you on that. They'll try to trick you between the N and the DF. Okay? Just be careful of that. Confidence level is not 74, it's 95. You got to put in 0.95. If you put 0.95 right there, it's going to mess you up. Calculate. There's your interval. 11.094, 12.906. Does all the math for you. You're expected to use your calculator. You don't have to. I use my calculator. You don't tell me that. Just put the darn interval. Again, it doesn't tell me DF. That's where students will mess up because they count that as a EP or I. Making sure you list the DF. So please put that DF. When you get your test, whenever that is, somewhere on there, make sure you put DF equals. So that you remember that you got to list that DF. So here we are. So all that work right there, I got to go back to a pencil. I already forgot. 11 something to 12 something?
Yeah, 11.094 to 12.906.
Beautiful. We are 95% confident that the interval captures the true mean, and again, guys, most of the time I'm going to go right here for the mean number of books read by all Americans. I'm going to go, that's when I put it in context, I'm going to put down what they asked me to do. They asked me to construct and interpret a 95% confidence interval for the mean number of books read by all Americans. That helps you make sure we're alluding to the population. So that's what I'm going to write. Go into that question and find out what you're going to write. Probably not 15 points anymore, probably not 12 points, probably somewhere around 10 points. But your next test, you're probably going to have a construct and interpret a something percent. Question? Not much new. T's instead of Z's. Means instead of proportions. How you prove normality is different. That's not different. That's not different. You still got to write a formula. It's different, but you got to make sure it's X bar, and that's T's, and that's S, and that's N. Values, which they'll give you. If they don't give it to you, if they give you the data, when you run the test, it will tell you what X bar is and tells you what S of X is. Let me just do that real quick because, like I said, your homework has to do that. So if you have the data, right, the first thing you'll do is stat edit. And you'll put your data in there, okay? Stat edit. Once you put the data in there, then you go stat test, go down to T interval. Don't use a Z interval. T interval, just go over to data. It won't ask you for X bar or anything else because it's going to calculate that for you. So if I go down to calculate, it takes a little bit. There's X bar, there's the standard deviation, there's 9. I had 9 sets of data. That means DF is 8. There's the interval. Do it again. I don't know, I just made up data. I had some in there. I just made it up. One sample T interval for mu, conditions, random, 10%, normal large counts met, right? There's X bar, there's the standard deviation. Table B, it's 1.962. With technology, it's 1.962. It's the same number, okay? Here's the interval, 11.9 to 12.91. We are 95% confident that the interval from there to there captures mu, the true mean number of books read by the American adults in the previous 12 months. Here's a little quick question on top of this, right? In 2011, Pew reported that the American adults read 14. Can we believe that 14? No, because it's not an interval, and that's all you got to say. No, I do not think that 14 is a plausible value. It is not in my interval. I do not think that 14 is correct. However, I could have just gotten a bad sample, right? We could have made an error. We don't talk about all that stuff with this. That's all hypotheses, right? 14 is not a plausible value. Therefore, I do not think that 14 is the true mean. Here's one here, real quickly. I don't want to do it the entire thing, but here's one where you have the data, okay? You have the data, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's not enough. So you got to put that in L1. Now, guys, let's also remember this, okay? After you put it in L1, you're also going to hit second y equals because you got to graph that data. You got to graph that data. So let your calculator do it. Second y equals, turn it on, I don't, for sure, don't use a scatter plot or a time series plot. I just go over and use a modified box and whisker like we did in chapter 2. I know that was forever ago. Box and whisker, you hit enter. It's going to ask you where your list comes from. It comes from L1. Frequencies, only one. Whatever you want to do. You'll hit graph. You probably won't see it. I see part of it. Zoom 9, because that zoom stats it. Beautiful box and whisker plot. There's no way I can think that that's abnormal. It's not skewed. There's no outliers. And then you got to transfer that to your paper. Okay, you don't get a chance to do that on homework very much. You don't, right? You don't transfer it. If you have to do that on my test, which you will, you got to transfer that on your paper to prove it. It doesn't have to be beautiful, right? I just put that down. I mean, that looks almost dead on. And then I just hit trace, and that's a 5. And that's a 3.5. So I just put those numbers on the graph just to prove I did it. Just to prove I did it, I just trace each one of those points, and I just write those numbers down on my graph. I don't draw. It's not a beautiful. They don't expect you to be precise or beautiful. They just want to make sure you did it. So I just put that on my paper, and I'll just put those numbers down. Okay. And then after you do that, that proves it. So that proves your large counts. Or I'm sorry, yeah, that proves your large counts. That doesn't really prove your large counts. It proves normality, I guess. Your 10% still going to be, because I'm sure 20 is less than 10% of all. And then it does your SRS, right? Random sample. Yeah, just throw it right there, hon. Beautiful. Okay, beautiful. Okay. Let's go back here real quick. Clicky, click, click. So they used a dot plot. I don't think I would spend my time writing a dot plot. Okay, again, box and whisker plot is just perfectly fine. One sample t interval, random, 10%. The dot plot does not show strong skewness or outliers, and that's all you have to say. Okay? I've never seen one show strong skewness or outliers unless if it's so obvious that they're going to lead you to it. I still have the formula. I still have the values. I still have DF. I still have a T critical value. I have my interval. I still have a conclusion. It's not enough to make a graph on your calculator when assessing normality. You must sketch. It does say sketch. It doesn't say draw. Sketch that graph on your paper to receive credit. You don't have to draw multiple graphs. Any appropriate graph will do. You have learned how different factors affect the margin of error. Those same factors still affect the margin of error. You need to know that, right? It decreases as your sample size increases, right? That margin of error will decrease if your sample size increases. We've talked about that many times throughout the year, okay? The margin error is proportional to 1 over the square root of n, right? I couldn't do a square root symbol. So if you increase it 4 times, it's going to cut the margin of error in half, right? Don't forget these type of things. So it's proportional to 1 over the square root of n. Quadrupling it will cut it in half. The margin of error is going to be affected with confidence levels, right? As the confidence level increases, it increases the interval, right? When I gave you plus or minus 10 years for my age, you were pretty confident you got it. When I gave you plus or minus 1, you were not as confident. 1, 10. You were more confident. As the level increases, your interval increases. It still doesn't account for bias, right? That has to do with the method. That has to do with the method. So if your sample is biased, your interval is going to be biased. If your sample is biased, your interval is going to be biased. That's not going to change anything. Okay? What else I'll say? Determine the critical value. I hope you know how to do that. I hope you can check and state the conditions, and I hope you can construct and interpret a confidence interval. With that being said, your homework for 9.1 should be posted on Achieve. I have it due Wednesday morning. Okay, I have it due Wednesday morning.